Hi all, very good morning.
Morning, Bharat. Morning,
Good
everyone.
morning. Good morning.
Yeah, let's give few minutes for others to join and then we'll get started. All right, let's get started. I'll just quickly start with attendance and we'll get started. All right, I think we can get started. I've marked the attendance, so we can get started. Just a second, let me share my screen. All right, so let's jump in and let's get started. So we will start with questions. So did you guys give a read about all the things we saw yesterday? Any questions that you guys have in what we saw yesterday?
But to me, it still need more time to understand and digest these skills. So this is the
Okay.
first time that for me. So I don't have any questions, but maybe in a later session I will bring it up if I have any.
Yeah,
So
yeah, sure.
I'm
And
little
generally
slow
what
on
I do
this.
is, yeah, generally what I do is after all the portions are done, right? I generally give two additional sessions, okay? So after all of the portions are done, I still give two additional sessions where, any specific topics that you want to, brush up on again. So I generally do those topics the last two sessions after all the portions are done. So my only request is as we are progressing through this, put in some of your time as well to, learn and understand and practice these things. So you will have more questions around that time frame. Okay.
Sure, Bharat.
All right, great. Anyone else? Any other questions?
Bharat, yesterday we did not touch up on transformers, right? We
No,
covered.
we have not yet. Yeah, we have not yet seen Transformers. That's what we're going to start with first today.
Okay, I think so far so good. Thank you.
Okay.
Uh, Maybe just to get a better context of what we are doing here, right? So what we are seeing here seems to be theory, Bharat, right? But
Yeah,
I just want to know how to connect this to the actual work that's happening in the
yeah,
companies
yeah.
in
So
developer
yes,
space.
yes. So this is all underlying architectures that we are learning, right? So we will be building a transformer-based text classifier. So we will not do this text classification, but rather we would do sentiment analysis using a transformer. Okay. So when you do that, when you build that, you will understand this. But in terms of coding any of this, it is no more than like, probably 10, 15 lines of code because everything has been like these have been built in like lines and lines of code and they've become big chunk of libraries. You just have to call them up with just like 15 different lines where you just given the inputs and it forms its own structure and then it works off of it, right? So that's why I'm not touching too much around how you actually do it in the companies as such because we will get to it. That's what we are here to learn for. But understanding this piece is very important so that uh, the 15 line of code, like I mentioned, is not a big deal, right? So underneath this 15 lines of code in the library, you may have like probably 1 million lines of code, which has all this logic, right? Inside of that, you may want to change something that might tweak your problem statement for your particular use case, right? As such. So that might add in more value to your business case, right? So in those scenarios, it's going to be useful. So that's why, understanding the underlying logic is important so that you will know where to look for what, right? You'll know what you're supposed to look for specifically as such, right? Because learning, just deep learning, right? Just simple deep learning itself takes about like 80 hours for you to at least go through the glimpse of entire deep learning, because there's so much in just the simple deep learning aspects itself. Deep learning, when I say, it's a simple multi-layer perceptron, and within that multi-layer perceptron, how things are, what is feed forward neural network, what is backward propagation. We just discovered at a high level what happens, right? But internally, how the values are computed, what is the formula behind it, how these things work in conjunction, right? And why am I doing such thing? Why this solution works? Um, so many such things. So there's like, even in just in terms of jargons, there's something called as softmax. There's something called as dense layer. There's a densely connected layer. There's something called as sparsely connected layer. Then there's something called as regularization. Within regularization, you have L1, L2 regularization, and then you have dropouts. And then you have the concept of these are all in basic neural network. And when you get to each and every individual neural network architecture, for example, RNN is a neural network architecture, recurrent neural networks, and then you have LSTM as another neural network architecture. All of these architecture will have all these, plus you will have the architecture's own specific items as well. And same goes for LSTM as well. So to understand it itself, just to understand this itself, it takes so many hours. So this is more of a glimpse in the course. So, there's some level of reading as well that has to go in so that, it's easier for us to catch up with everything as such. Guys, so that's the only thing that requires. And people say you don't need to learn at this level. My thought process is again that coming up with such architectures in the future will only enhance AI's performance. And it's not just that, it's going to be such a way that companies are going to companies are going to want people who can do it at this level. They understand, if I turn this knob, this is going to change. And if this changes, this is the implication that I'm going to get, right? So they want people who can uh, experiment at the lowest level of neural network architecture itself in order to get through all these things, right? So that's going to be the future. So that's why I'm explaining that, at this level, learning is good. The more we see this, don't worry, the more we keep seeing this, the more you will get through these items as well.
Okay, thank you.
Got it? Yeah. All right. So before we get into transformers, we are going to see something which is very important. It's called diffusion models. Okay, so what are diffusion models? So diffusion model has its own, again, neural network architectures. Um, Diffusion model first started with autoencoders, then it evolved into variational autoencoders. So basically, autoencoder is basically encoder, right? So we will see how that encoder works, right? And then it evolved into variational autoencoder. This evolved into generative adversarial networks and generative networks. In generative networks, typically decoders are used. You will understand why generation and decoding are in conjunction. and encoding and shrinking are in conjunction. Okay, we will see all of that. Okay, so what are autoencoders? Autoencoders are very, very simple concept. Okay, so what did we see in neural network thus far? We created a list of neurons, right? We created a set of neurons, right? And what did we do with those neurons? Just a second. What did we do with those neurons? We put them into our final, what do you call it? Outcome, right? So here we had our outcome, and here we had our X, right? And in between, we try to form a formula between Y and X, correct? Y is a function of X. I mean, when I say X, it means all different X, like X1, X2, X3, X4, X5, right? So, and we try to form a formula of Y and X over here, right? That's what we were trying to do. So what all different types of machine learning problems did we see? You guys remember? I'll start with one. You guys can tell me more. Supervised was one machine learning type we saw, right? What other types did we see?
Unsupervised, semi-supervised.
Yeah, unsupervised and semi-supervised, right? We saw these three types, right? So what is supervised? Do you guys remember what is supervised?
It has some set of inputs and previous history as well. So based on that, we
Yes,
can factor.
you have inputs and outputs. Basically, you know what is the source data and what you actually want to predict. You have both the information in place. What is unsupervised? You just have the inputs and you want to find a pattern between the inputs, or you want to basically shrink the inputs, which is called as dimensionality reduction. We saw this, right? Pattern is basically pattern mining. We saw FP growth and other algorithms here. And then what is the other type, which is clustering, grouping, grouping the set of inputs into clusters or bucketing them, right? Automatically. So for this, we use clustering algorithms, right? Yeah, semi-supervised is not important. So how can you use a neural network architecture for thus far we saw we used it for supervised problems. How will you use it for unsupervised problems? So that's where variational autoencoder comes into picture. Okay. So there is no Y, no concept of Y. So what happens is variational autoencoder has a encoder decoder architecture. It does not only has encoders, it has an encoder decoder architecture. Okay. So this is how your variational, this is how your autoencoder as well as variational autoencoder works. Okay, both works. So basically, what are we trying to do over here is till this place where you are reducing the number of neurons. This is called your encoder. Where you are constantly increasing the number of neurons, this is called your decoder. And this place, the in-between place, right? The innermost hidden layer, this is called latent space. Okay, what are we trying to do is we have X1, X2, X3, X4, and X5. Okay, we shrink the 5 different inputs into how many inputs are we shrinking it into? This is just getting shrunk into 3 different inputs, right? It is getting shrunk into just 3. And then we are expanding back that 3 compressed data. We are expanding that back into again 5 different inputs. And we want to compare the same input I gave. Did it come out as the same outcome? What is the difference between X1 and X1? So let's say X1 inputs are 10, 215. Here you have 3, you have 54 and 71. Output you're getting like 9.8. Here you're getting 202. Here you're getting 2. Here you're getting 31. Here you're getting exactly 71. So then you compare this outcome with this outcome. Basically, you're trying to predict the same inputs over here. All right. So you understand what is happening here. What is the use case? What is the benefit out of it? So we're just predicting the same stuff. What is actually happening here? Right? That could be our question. So we will talk about this. Just remember this latent space. We will talk about this in transformers architecture. Okay. But if you're able to, and then you compute something called as VC loss, right? So here you compute something called as reconstruction loss. That is the loss that you compute here. That means you're reconstructing the same input over here, right? So you're just trying to form the 10 as an output here. So for that, you again work off of the hidden layers to come up with a formula. You adjust the weights and biases of hidden layers to ensure that the same value that you sent in is coming out of this. Okay. So once you have trained such a way that the reconstruction loss is just 0.001%, that means what can happen in real world? You can completely remove these two. You can just use the middle 3 layers in order to form outputs like this, right? Right? Basically this itself, these 3 layers itself is equivalent of these 5, right? You have shrunk the 5 in such a way that without any, this is like, just imagine it like zipping a file. Okay. If you zip a file, you have lossless compression, right? Where you don't feel, you don't have any sort of loss, but you try to allocate the memory in such a way that there is no loss as such, right? Imagine this is a very similar process, but this is with actual data. So with your actual data, you are able to come up with some sort of just 3 inputs. You have shrunk the 5 inputs to 3 inputs, wherein you're meaning to say that just these 3 inputs are representative of all the 5 inputs. That's what is the underlying meaning of it. I'll pause here. Any questions here?
But one doubt.
Hmm.
So the 5 got shrunk to 3, right? So, but
Hmm.
you had one more hidden layer of 4 neurons.
Yes.
Now you are telling like that 5 output is as good as your 3 output.
Yeah.
But if you're cutting down that 4 neurons, which is a hidden layer, the output which is coming to 3 neurons will not get disturbed.
It can. Yes, that's a valid question. Yes, it can. It also depends on all these layers. Okay, so you may have one more layer here, which may have probably 8 neurons, right? You may expand 5 into 8, then shrink it into 4, then shrink it into 3, right? You may have like that as well, but that is not like a auto encoder. That is not an encoder practice. Encoder is constantly you're shrinking this. That's it. You shrink them, right? So you can keep, but to answer your question, yes, it is dependent on this 4. Yes, you're right.
Okay.
But the 3 is the ultimate one, right? Because once you get like a reconstruction loss of 0.01, that means the 3, because the 3 is only expanding to 4, right? The 4 is not expanding. The 3 is the one that is expanding to 4, which is creating one more additional variable. And the 4 is again expanding to 5, right? That means the 3 is the core area, right? So that's why we call them as the most least variable set or the compressed features, right? That's why it's also called as latent space.
Bharat, what is the name of this in overall?
This is called auto encoders.
I think the example which you given, the zipping, unzipping, right? That is typically matching with this.
Yes,
But
yes,
other
that's correct.
than any other examples in
Yeah.
our
I've not yet gone into the actual examples. So the
okay.
actual real world examples is what we're going to go next. But so far, any questions here?
One question, Bharat. Here
Yeah,
we are doing auto encoding, right? While doing
yeah.
an encoding, any data I'm feeding it, it will do the encode and decode. To the max, how many layers it should auto encode? It will decide on its own till it reaches that reconstruction level 0.0, right?
No. We have to design
Uh,
it. So we
we
design
have to
all these
design
things.
them.
Like how we designed the tensor in TensorBoard we designed yesterday, right? Like that, we have to
Mm-hmm.
come up with this architecture. You may have, let's say you have um 20,000 inputs. I'm just making it up. You have
That
20,000 different.
reconstruction.
Yeah, so you may have 20,000 inputs, let's assume, okay?
Yeah,
And
yeah.
you can come up with an architecture where you shrink 20,000 into, let's say, 16,000, then you shrink it to 8,000, then you shrink it to
Mm,
4,000, then you shrink it to 1,000, then you shrink it to
mm.
256. And typically having your neuron size in the power of 2 works really well. I'll give, when I give you the cheat sheet, you'll understand why I'm saying all these things, okay? 256. Then from 256, you can shrink it down to, let's say, 64, and that could be your
That
least.
latency space should be reached.
Yeah. You
Mm-hmm.
you have to design
Okay,
the.
okay.
You can decide the number of layers. You can decide the number of
Mm,
neurons in each layer. So both are done by you.
mm-hmm.
So you can try out different
Mm.
combinations. You may not know which will actually reduce the reconstruction error, right? You have some intuition around it, which I will share in a cheat sheet. Okay.
Okay.
All right. So this is about it, right? Now, looking at this on a real world use case, right? So let's take the case of server down. So in case of scenarios where your server is down, right? Or your server drops off, right? Or your server fails, right? Say, for example, you have an application hosted. You don't know, you may not know at what kind of load your server may fall out, or when this can happen. This is one scenario. The other scenario is, these are all like once in a blue moon kind of an activity, right? The second activity, a fraudulent transaction. You don't know when a fraudulent transaction works, correct? When a fraudulent transaction comes in. What is the problem with these scenarios? What do you think is the problem with these scenarios? You do not have historical data. You may not have good historical data. So let's say when on a daily basis, 10 million transactions are happening. How many fraudulent transactions you think it may come in per day? Max 5 transactions. This could be the ratio, is what I'm saying. 5 transactions out of 10 million transactions is going to be the fraudulent transactions. Then how can you build a model to identify frauds? Because you don't even have that much amount of data to train your models, right? You see the problem here? The number of fraudulent samples or number of fraudulent records or the number of fraudulent um cases or scam cases of transactions are very less compared to regular transactions, right? You guys all agree with me?
Yeah.
You guys
Yes, Bharat.
understood what I'm saying here?
No, Bharat, not exactly. But how this can be an example for our auto
Yeah,
embedding?
yeah. That I will explain. But did you understand? Yeah, that I will get to. That, hold on with that. So that's a
Okay.
little tricky to understand.
Mm-hmm.
But out of 10 million transactions, very less amount of transactions are only fraudulent transactions. So you do not have a data set of fraudulent transaction to go with supervised learning. You guys agree with that?
Got it.
Yeah.
Everyone agrees with that, right?
Yes, Bharat.
Yeah.
Okay. So the idea here is how you can use autoencoder for this is one of my specific patent also was on this is how you can use autoencoder is you take this 10 million good data set, right? And you try to replicate the 10 million good data set over here. And you just, shrink it and then expand it. Okay. Once you get like a very good reconstruction error, that means you can say that your entire neural network has gotten accustomed or adjusted to the good transactions, correct? The idea here is when you give a bad transaction or you only trained it with all good transactions alone, you have not yet, the intuition is you have not yet trained it with any bad transactions with this. You have trained with complete all good transactions alone in your entire neural network architecture. Okay. Now, when you feed in a bad transaction for that one single record, when you try to inference for that, you will get a high reconstruction error because it will not be able to properly reconstruct a fraudulent transaction, but it will be able to reconstruct good transaction well because you've trained it only with good transactions. You see the idea here. In real world, you will train it with this model would have been trained with 10 million per day, right? So let's say in a month you have 300 million. Okay. And then in a year, how much you may have? You may have 3.65 billion. So 1 year's worth of transaction, you would have trained it with this autoencoder. So now this autoencoder, whenever a new transaction comes in, you put it through this autoencoder, you check the reconstruction loss. If the reconstruction loss is below, let's say 2% or below, let's say 1%, that means it's all good transaction. You can set a threshold over there. If the reconstruction loss is going above 1%, that means you have to really take a look at that transaction. That transaction is anomalous. That's what you say. You don't say it as a fraud, but you say that that transaction is anomalous. That means that transaction is somewhat weird or that transaction is a little bit different from this 365 billion transaction. Why we say that it is different? If it is not different, our model would have been able to reconstruct the same inputs back again. But it is reconstructing a good input here, whereas we have gotten a bad input here. That's why the reconstruction loss is going up. You see the point, right? With an example, let me explain. So let's assume all these transactions, 365 billion transactions would have happened just as a case. I'm telling this, okay? With you have a feature that says home IP address and transaction amount less than $10,000. And then you have another feature which says, which is for, um, let's assume logged in from a different device. Logged in from which country? So these are four features you have. Your feature values are this is US because you're doing it for a US bank, and home IP address is same is the input you're getting. Sorry, different is the input you're giving. Different is the input you're giving, and then you're giving less than $10,000 is false, and then different device is true. But when it reconstructs the home country is US and the transaction also happened in US. Okay, so this may, when it reconstructs based on the 365 billion parameters, it may reconstruct this as US. It may reconstruct home IP addresses, yes, or same. The next would be true, with less than $10,000 would be true, and the different device would get formed as false. So this would increase the reconstruction loss because this is the input we gave, but we got a different output that got formed from the hidden layers, right? So that means this would increase the reconstruction loss just for that one transaction. For every new, once you've built the model, you will test the model, right? When you test the model with upcoming transactions, when a transaction is happening right now with a bank, let's say, you inference the model, right? You send that input to the model, you get the output from that model, right? That output, when you get it, you may have a high reconstruction loss. When you get a high reconstruction loss, that means that transaction is a anomalous transaction, and that transaction may or may not get into a fraudulent scenario. But that is a good way of catching these fraudulent transactions. You see how we are using it? I'll pause here. Everything I wanted to say I've said. So I'll pause here. Any questions? You guys get the idea of how we are using it?
Yeah, I mean, Bharat, it's actually what you have said is okay, but maybe I'm not able to connect it to the problems that we actually solved during supervised, semi-supervised, or unsupervised category. So, okay, like I think first we started with the X and Y, right? Like wherein
Yes.
we gave some set of inputs and we had to get some set of outputs with them, and we were trying to adjust the weight and bias in last class and arrive at the output or predict the
Correct.
output.
Correct.
but,
Correct.
but now we seem to be doing encoding and decoding, wherein we are saying we are regenerating the inputs, right? So I think I'm not able to understand that
Okay.
part
The
properly.
simple thing is the output you get y here, right? So this is still y. If you imagine this is y, you just put y is equal to x. So you what you do, you send these inputs 10, 2, and 5, 3, 54, 71, right? You initialize random weights over here, correct? For all the hidden layers, you initialize random weights. Okay. You may get some random outputs here, right? You may get 320, you may get 415, you may get 22, you may get 74, you may get 800, like that. You may get different outputs. Then what you do is you compare these outputs with this inputs, right? And based on that, you adjust the weights back again.
Right.
So it is not just a separate output, but rather your output is the same input. So you don't want 323 here, but you want 215 here. So for that, you will adjust the weight. You don't want 412, you want 3 as a output here, right? For the third element. So for the fourth element, you want 54, but you've got 45. You, instead of 70, you may have gotten 800. So you try to accommodate for that and you try to work off for that. That's all. It's nothing
Okay.
complicated. Same concept. Instead of y, just assume the values here that you would set it up as x itself. That's it. When you code it, you would code it in that way. That's it.
Okay. Okay.
You are able to connect it now.
Yes. Yes.
Yeah,
Yeah.
that's it. As simple as that. Yeah.
Okay, so when you talk about the final use case that you explained, right, wherein we wanted to identify the fraudulent transaction, so are we
Yeah.
saying that in the case of fraudulent, those five erroneous or fraud cases, when we apply the same logic, we won't be able to get the input just for those five cases?
Yes. Yes. Yes.
Okay.
That's why I showed with an example here. So if these are kind of your features, if you send these as your inputs, because it has been trained on 365 billion parameters, which has not seen some combination like this, it will not generate a same combination. It will generate home country as US. This is equal. Whereas home IP address may be yes in most of the cases because we have trained it only with clean data set, regular transactions, right? And then greater than 10,000 value maybe true. This could be your output that comes out of the autoencoder, not the input that you send, but this is the input that you have sent. And is it a different device? No, it is not a different device. But here it may say it as yes, it's a different device. Your input is yes, but your output you got out of the autoencoder is no. So this is not equating, this is not matching, this is not matching, this is not matching, this is matching. On a simpler note, your reconstruction loss is short up by 75%, right? So 75% has error, only 25% is correct, right? If you, it won't go up that much level and all of that, but just as a case, I'm just trying to explain you how you can actually identify anomalous transactions. That's it.
Okay.
Yeah. Any other questions? Anyone else? So you guys are all clear with this? No questions. Is it good?
Good, Bharat.
Okay. All right. Fine. Then. Great. So let's continue to move further. Right. So ideally, this is your autoencoder. Okay. Variational autoencoders, again, it's going to be a little bit complicated to understand, but just stay with me. Okay. So what do we do here? This is your latent space, right? If you sample from your latent space, that is called variational autoencoder. I'm just telling you the explanation.
Bharat, one small suggestion. If you're going for a
Yeah.
new concept or a new example, just can you put it in a different
Yeah,
page
yeah, yeah.
or at least below than this one?
Sure. I'll do that.
Thank you.
Okay. So variational autoencoders are nothing but from your latent space, instead of directly sending all the records, you sample from your latent space. This is a book explanation. Okay. If you sample from latent space, that's it. Everything else is the same. What is sampling? How that works is what I'm going to explain right now. Okay. Nothing else. So in terms of book, the only difference between autoencoder and variational autoencoder is that you sample from your latent space rather than sending all the exact outcomes over there. Okay. So now we have to understand how the forward and the backward propagation works a little bit more. Okay. So you have your training data set, right? So let's say how many records you may have. You may have five inputs, right? X1, X2, X3, X4, and X5, right? You may have five inputs here, correct? And you may have a Y here, which is your, sorry, this one doesn't have a Y. I'm sorry. Yeah, you have X1, X2, X3, X4, X5, right? So you have five inputs here, right? How does your training happen? So do you guys know what is training and testing phase? Anyone here knows what is a training and testing phase? So what do we simply do here is, let's say you have five records. So what did we speak? We spoke that 3.65 billion transactions are there. That means 3.65 billion records will be there in your table. This is your data set. So this has 3.65 billion records of good transactions. You guys all agree with me? You guys understand what I'm explaining here?
Okay, Bharat. So far good.
Okay. So what are we trying to do here is with these 5 features, 3.65 billion records, you can't pass all the records at once. You can't do that at once. You can't pass all your records at once and get through an epoch, right? So to get through one epoch itself, you split this into batches. Okay. So you may batch this 3.65 billion. Let's say you may batch it out like, 36,000 records per batch. And you may run, I don't know how many batches, it might go very, very high. So let's say 10 is 360K, 100 is 3.6 million. 100,000 times you would do this. Per batch, you only consider 36,000 records and you do this process 100,000 times to complete one epoch. For every epoch, you will run through all this data set, all the 3.65 billion records. But you can't just run, you can't put through all 3.65 billion records and adjust wait for all of them, correct? So you would just do them in batches. You guys are getting what I'm doing here. You're not sending all the rows at once to complete a forward propagation or a backward propagation. For doing a forward and a backward propagation, you split the rows like this. You send 36,000 rows and you send that 100,000 times in order to complete the 3.65 billion rows. That is how you would do it. You guys get it? Or you don't understand what I'm saying?
Got it, Bharat. So instead of sending not instead of, we cannot send all the 365. So we are splitting it into some set of
Yes,
data,
yes,
and each time we'll
exactly.
get a different set of output only, right?
We will not get different, yes, I mean, obviously different outputs would come in, but you should not understand it that way. For that 36,500 records, you will get 36,000 records, you will get 36,000 outputs. For the next
Okay.
36,000, you will get the next 36,000 output. That's how
Yep,
it
yep.
works.
Okay, got it.
Okay.
Hmm.
So, and
But
then
why are we?
completing, yeah.
Sorry, after you.
No, why are we doing this is it is computationally exploitive. If you do all at once, you don't have any system that can compute at that scale. So that's why you do it in batches so that you can get through the computation because we do heavy computation, right? We want to compute new values, and this is just one epoch, by the way. So one epoch we ran yesterday, right? Um, One epoch you saw yesterday, right? Over here, sorry. Yeah, this one epoch, right? 13 epochs meaning it is splitting it for this data set size is very small. You see the batch size here. So let's say if this data set has about I don't know how many inputs it has. Let's assume that this has about 1,000 inputs. If the batch size is 10, that means it splits it by 10 records per batch and it sends it 100 times to complete one epoch. So every epoch, all the 1,000 records happens because you can't do computation that quickly for this huge data set. So you'll always split them into batches and work off of batches. All right, does that make sense?
Yeah, it makes sense. So who defines that? What would be the threshold for each batch?
You define it. So that's also a parameter. So you define it when you code it, you say that, okay, I want to give 20 as the batch size. I want to give 15 as a batch size. I want to give 10 as a batch size. And again, batch size also, if it is to the power of 2, it works really well. It's because why we always have neurons, batch size, everything to the power of 2 is because these goes and the hardware that you have is also built on that fashion, right? So it can exactly use those hardware points in order for computation, in order to get through things. We run it directly on the GPU hardware. So the GPU hardware is also built off of two power items. All the bits are in the powers of two. So because of those reasons, it can actually work really well in that fashion. So that's the reason you always keep your batch size also in power of two, your neural number of neurons in a layer in power of two, and so on and so forth.
Now, okay, got that. So, one more doubt would be, Bharat, like, let's say the batch size which we would have done, it's actually, a huge batch in
Hmm.
terms of the number of items. So, is there any notification or something gets popped up which, gives us a trigger that, okay, maybe we would have given more in one batch? So, does it make
Uh,
sense? No?
I didn't get your question. So it
No, so,
when yeah, go ahead, go ahead. No, you go ahead with your question.
so the batch size, let's say you are showing on the screen is 12, right?
Yes.
Now, let's say being new to this current scenario, I put it as 50. Let's say
Okay.
50, right? So I put 50, but the output is taking longer time. Does it mean like, I should rethink on the number of items in single batch? How do I get into that conclusion that, number of items in a single batch is actually larger?
Again, that is, yeah, again, that is also very experimental. That is also experimental actually. So that's the reason we get the knob to control this, right? It depends on your problem state. Why do we have to define all of this? Have you ever, just imagine this, right? Why do we have to define the number of layers, number of neurons? What is my batch size? Why do we have to define it? It's because for every problem statement, for every data set, for every way you treat that data set, it is all experimental. Nobody can definitively say this is the batch size, this is the number of neurons, this is the number of hidden layers. That's why the architecture is so complex that you have to define, experiment through all these things in order to come up with the final solution. But batch size is more of a trade-off. If you keep a higher batch size, that means you're at one batch you may have to do heavy computation. If your batch size is too small, it is not going to learn anything out of one single batch as well. So a batch should be a representative of good set of data, not too less, not too high. So it should be a balance within that. And ideally keeping a batch size of at least 2 to 3% of your data set size is good. Again, this is my numbers. It depends on your overall data set size as well. But if your overall data set size is less than, let's say, 1 million records, keeping your batch size up to a maximum of 1,000 is good. Yeah, it's 0.1% to 0.2%. That's it. Not 2%. It's 0.1 to 0.2% of your data set size should be your batch size. That's it. And this works only within 1 million records of your data sets.
Bharat, is it mandatory that all the batch size should be same, exactly same, or it can be more or less?
No. When you set the batch size, when you start training, the batch size is always set the same for this architecture. But let's say for a different problem, for the same data set, you can try it with a different batch size on a different training. You can try experiment keeping 16 as a batch size. You can experiment with 5 as a batch size. So you can experiment it, but once you've set it for that entire training process, the batch size is the same. You can't change the batch size between epochs. You can't do
Okay.
that
Mhm.
because it will also confuse the system. There's something called as uh, note this term down. There's something called as batch normalization. If you know what is normalization, you guys know the bell curve, right? You convert that, let's say this batch of data set, you apply a normal uh, curve on top of that, you arrange the data in a normal curve fashion, and then you send it to the neural network. So you allow it to follow a normal distribution, and then you can send it to that's a little complex concept within the batching itself. So that's called batch normalization. You guys can give a read about batch normalization. So you will understand how batching and batch normalization can be used as a powerful tool when it comes to neural network.
Okay, Bharat.
Any other questions?
So, what is the expected? I mean, is there any expected outcome at the end of training the 36K records every time?
Yeah, the outcome is the same. In autoencoder and variational autoencoder, the outcome is same. The reason I was talking about batches is, okay, so this is the reason I was talking about batches. Okay. So I said something called as batch normalization, right? So what happens is you send in one, it is not an epoch, it is in it is a percentage of one epoch. Okay. You send what? You send 36,000 records here, correct? And then you shrink it down into 36,000 records, but just 4 dimensions. One dimension is cut off. New 4 dimensions are formed for the same 36,000 records. For the same 36,000 records, 3 dimensions are formed. One more column is cut off, right? Right? You guys get it till here, right? Now, within the 36,000 records, you directly pass the 36,000 records to form fourth dimension again back, right? That's what you're trying to do over here, right? But instead of that, you don't send the 36,000 records, but you consider this 36,000 records as it's following some sort of distribution. Do you guys know what is distribution? Do you guys remember the uniform distribution, normal distribution? Do you guys remember the bell-shaped curve? Do you guys know what is distribution? It means it follows a specific pattern. So you know where the next data set is going to come in. So you can just apply, yeah, leave of distribution. So I'll not even confuse you to that level of mathematics. I'll just keep it at a common language sense, because if I get there, it's going to become more complicated for you guys. So I'll keep it very simple. Okay, you have 36,000 records, right? You don't send this 36,000 records, but you sample some records from this 36,000 records, and you send only those samples over here to the next thing. You don't send all 36,000 records there. This is only during the training process, not during the inferencing process, only during training process. So what happens when you just sample and send some additional data set? It forms, it may form its own record based on the 36,000 records. It may sample within the distribution and form its own record, and it may send that record over here to the next level. So the model gets more generalized. That means if you have trained it with, even though you have trained it with good transaction, if all the transactions are just from United States, it may not work well for European data sets, right? So it may work well for European dataset as well with variational autoencoders. It helps you to generalize your model. What is generalization? That means your model is not confined to work in just one domain or one single space. It may be able to explore to much more area of scope. In order to improve the generalization factor, you can use variational autoencoder. You don't send this 36,000 records, but you can define how this 36,000, what sort of a distribution this 36,000 records are following, and you may sample any 36,000 records from this distribution. With the 36,000, you may form a sample, right? And I mean, you may form a distribution. Distribution is continuous. So let's say you may have data points only in the dots that I'm mentioning, but other places apart from dot here, there are no dots. It may pick records from here as well. Since it is following a normal distribution, it may pick records from here as well. And those records can also move in here, which can help you to add more data to your data set as well. Add more data to your data set as well. And it can work off of any similar data set as well. Any data set that comes in, it may be able to accommodate for that. This might be a little hard for you guys to understand, but I'll pause here. So I'll open the forum for questions. So I can answer questions. At least that may help you to understand this better.
Uh, so maybe I think okay, like let's say we do the iteration with 36K records, right?
Yeah.
And then we keep doing it for every 36K.
Yeah.
So, um, like, I mean, what are we expecting at the end of completing all the 100K iterations, right? Like, I mean,
So
how can
when one epoch is done, the same forward and backward propagation happens. When 100 epochs are done in forward propagation, what do you do? With random weights, you generate outcomes. You generate the outcomes for all 3.65 billion records. These 5 features, this exact table will be replicated. This exact table will be replicated over here. And then you compare these two tables. Then you make adjustments to the weights in the backward propagation. Then in the next epoch, you try to form a table again with 3.65 billion records. Then you do a comparison. Then based on that, you adjust the weights. So that's the entire process.
okay, the problem I have is like they are getting trained in small subsets, right? Ideally, they all have to work together, no?
Yes, so the neural network, the base architecture that has been pre-built by libraries have accommodated for all of that. So let's say they take care of, you just have to specify the batch number. You don't need to worry about how the batches are working internally because they've already written the code for all of that. So they will adjust all the batches, they will normalize all the batches, they'll get the consolidated feedback across all the batches. Based on that, they will update the weights for the entire data set. So all of that coding has been done in terms of bringing in parallelization and all of that. They've brought in all those things and they've done that.
Okay.
Any other questions?
Bharat, one more question. If
Yes.
we add one more data, then how it will be? Can we increase the x1, x2, x3? It's a default we have fixed it previously, right? Can we increase it to x6, x7 like that? We can increase it, or you can use the same? Yeah.
You can increase it. That means your input layer and output layer will also increase.
Iteration will be, is there any maximized, maximum size, it will be iteration this based on the data only, right?
Yeah, you can see it all depends on your computation. You can, if you have a, if you connect all the GPUs in the world, you can go to any level, right? That is how it works basically. If ChatGPT is doing some computation, they are building their ChatGPT architecture only for the amount of GPUs that they possess. So that's how it typically works. That's all.
Okay.
You need to have the infrastructure to support your architecture. That's it. The more the complex the architecture becomes, the more better the results can be. But you need that computation. That's it.
What I am thinking is, if we increasing the iteration, there will be any slowness will be happened like that. We are currently I'm working in server side. That's what is there any performance issue will be happened, or like that?
See, that's what I mentioned. So here, as I'm completely, so you see this, right? This is loss getting reduced as and when every single epoch is running. So for 17 epochs itself, I achieved a test loss of 0.331, training loss of 0.316, right?
Yes.
But now it achieved in 67 epochs itself, I achieved 0.1% loss. That means the system is 99% accurate, 99.9% accurate. So I can stop here. I can stop with 67 iterations. So it is up to us to understand when to stop this execution process as well. So when ChatGPT kind of companies, Gemini kind of companies are training as well, they will have a epoch set where they will also stop it. Beyond that, they will not run it.
Oh, okay, got it.
Yeah.
Thanks.
Any other questions?
Sorry, just to understand clearly, like you said, one epoch happens when we complete all the 3.6 billion
5 billion.
data
Yes, correct.
once, right? So,
Yes.
like that, I mean, we keep doing that again and again to achieve this percentage.
Yes. Yes, exactly. Yeah. So the 3.65 billion records are predicted and the 3.65 billion new records are generated. We compare them both and then we adjust all the weights. So that is one epoch. Again, you do this process, that is second epoch. Again, you do this process, that is third epoch. Imagine how computationally exploitive that is. So that's why they say, ChatGPT has been trained on, uh, let's say, when they say 50 billion parameters, this is what they mean by that. 175 billion parameters they've been trained on. So this is what they mean by this.
Okay.
So it is simply the number of rows of data that you have in order to train. But over there, it's a little different, but you can for now understand it as the number of rows that you are using to train the data. For now, that is fine because over there, it will tweak a little bit, but that's very much the same because of the type of data. All right, any questions thus far?
Bharat, these two types, right? That auto embedded and variant auto embedded. This comes under, I mean, is it a different types of neural network or?
Yeah. So that's what we started with. It's diffusion models.
Okay,
Autoencoders,
okay.
variational autoencoder comes under diffusion models.
Thank you.
Yeah. So we also have GAN, which we will cover in section 4 separately. But I just wanted to cover diffusion models as well before we jump into transformers and attention models. So I wanted to jump a little bit into the diffusion models and then come back to transformers and attention mechanism. All right. So yeah. So
But
now, yes, go ahead.
one doubt, sorry. If you could go back to that neuron screenshot, like
This one.
no, the epoch one. Uh,
Yeah. Yes.
so here, if I understand right, so the test score, in order to get the desired test score, we will have to do an epoch. An epoch is nothing but going through the data again and again to get the desired test score, right?
Going through the epoch just once is one epoch. You have
Correct.
to
So,
do multiple epochs in order to reduce your training loss. So in my first epoch, let's say in my first epoch, I got I was getting a test loss of 15%, right? And
hmm,
then in my let's say in 22 epochs, I'm getting a test loss of just 1%. And then in my 33rd epoch, I'm getting a test loss of 0.4%, right? And then in my 68th epoch, I'm getting a test loss of 0.1%, right? So the more the epochs run, the more ideally your loss should go down because your weights are being adjusted. For one epoch, you predict the output, and then based on the output that you're predicting, you adjust your weights, right?
yeah.
So this is
Okay.
what happens back and forth.
So epoch actually helps the hidden layer to work and get or reduce the test loss. So if I run epoch first time, as you said, right, my test score could be 15%. If I run it again, it could be 10%. Then slowly
Yeah.
it will come
So
down below
yeah.
1%.
So that is the piece because so random weights are initialized, right? So every time I refresh it, you see different test losses because random weights are initialized first, right? Now you see 506, right?
Hmm.
If I refresh this, 499, 501, 499, 498, 501. Every time random weights are initialized, right? And if I reduce the number of neurons and all of that could change because it's just random weights. If I just
Got it.
remove, yeah, if I just have it like this, you see different. 5.6 or 56% also came in between.
Hmm.
So these are just random initial weights that are getting assigned. That's it.
Okay. Yeah.
Yeah. You see 6.01 also came in, right? So
Hmm.
because the initial weights are random, and after that, over a period of time, that weight gets you see here, it is still learning, but this activation function is not able to solve it, and these many number of hidden layers are not so helpful in solving this, right? So that's
Hmm.
what is happening here. So any questions thus far? Any questions?
Yeah, good work.
All right. Also, this is one piece where, ReLU is kind of, it is actually non-linear, but it is kind of linear. So basically, that's why you see, the lines being like very straight lines which are defining it, right? Just a second. This is not even able to solve it. ReLU can solve it, but it is kind of linear. So that instead if I use tan h, this becomes non-linear. When I say what is linear and non-linear, you guys understand, right? It's curve versus direct lines that you see. When it forms a boundary, this is a little bit curvish. Whereas if I form it with ReLU, it's more of a line-ish boundary. So that is called activation function, which we'll get. But yeah. So coming back to the topic, any other questions here?
The
And what
different
we saw this.
activation models that you showed, right? Like, is that something that we have to learn, Bharat?
Yes. So yes, there are. I will give you a cheat sheet like this. There are about at least about 100 different things that you will have to go through. Um, for example, learning rate is alpha. So let me just see if this, yeah, let me show you this. You guys are still able to see this. I wanted to show it to you in a three-dimensional graph. Yeah, this is the actual graph. This is how just a second. I don't know what is that. Yeah. So you see this, right? This is how your error is generally plotted. Okay. There's something called a saddle point in this. Saddle point is like when you sit on a horse, you have like a saddle point, right? So like that, there's something called a saddle point where it gets stuck. It will not be able to reach to the lower point. And that's how evolving AI is. We were in a saddle point in like 2, 3 years back in terms of AI itself. And we have achieved a really good global minima today that all these AI models are performing really well, right? Um, so like that, there are so many such concepts. Um, Learning rate, there's momentum parameter, there's activation function. Within activation functions itself, you have at least 100 plus varieties of activation functions. What activation function is to be used at what place for what purpose? Softmax layer, there's different types of layers of neural network itself. Convolutional layer, um, you have recurrent neural network layer, you have LSTM, you have so many such layers itself in neural network. Then within that, you have just an image use cases. You have something called as striding. You have something called as pooling. You have something called as um it's even hard to remember all those concepts. So I will give you a cheat sheet of different things, why it is used, where it is used, what happens if you increase the value, what happens if you decrease the value, with all the most bare minimum items. Okay. I'll give you a cheat sheet. So that if you can get through that, that is more than enough. That is something to remember and all as such.
Okay. Thank you.
All right. So any further questions? Any other questions that you guys have? And don't worry until just bear with me until just section 4. Only section 3 and section 4 are theory heavy because these are the underlying concepts of all these big large language models that you see. Okay. The more you understand this theory, the more you become a complete AI person who can if you just keep practicing this over a period of time, you can start to build large language models itself. Right? So that's the power that these concepts have. We will discuss real world applications at the end of section 4. That is where you will be able to connect all the dots. And from section 5, it's straightforward. It's like complete application oriented stuff. We will play around with prompts. We will start to build we'll start to use LLM APIs with OpenAI APIs. We'll build agentic system in section 7. Then we will be using Hugging Face, how you will download a pre-trained model, how you will use a pre-trained model and so on and so forth. That's what we will be seeing in these sections.
Bharat, Kumar is in here.
Yeah.
So in the section 3, we today we plan to like set up this lab session for this transformer, right? That lab session experimental thing. So now everything is going as a theoretical. Like that's why the understanding is little challenging. So if we start do actual things, then we could have some better idea. At least
Yes.
20%,
So the
30%.
difference is the difference is though you do the lab functioning, right, you may
Mm,
not basically you will generate most of the code for the transformer. Okay.
mm,
And the second piece is you may not touch at this level itself. For transformers, the inputs are completely different. So you will work off of a different thing as such. So you will not find a direct relation as such with what we are seeing over here. Okay. So the coding part is just going to have very high level. You may not see at whatever level we are seeing over here. So that is also going to have a small level of gap because if you really want to learn that, you may have to start coding this from scratch, which is not required, right? Which is not required. But when you learn it at that level, that's when you can actually do it with hands-on. But hands-on does not have too much of a co-linking with just in this topic I'm meaning to say, but other topics it is different. Okay. But in this topic, this is how this typically works.
No, let
But yeah,
it
but let
be.
me,
See,
I'll see how I can integrate it and how I can, provide you some more inputs on this front.
yeah. We anyhow we are going to do this lab session, right? And also,
Yes,
if
please.
when instead of like deep diving this R and all this like architecture, like if you give like if you give do something practical, then it is more easy to understand. That is what I'm saying.
Sure, sure. See, yeah, sure, definitely. Yeah, we will do that. We will do that.
So next class, are we expecting to do this lab session?
Next class, we still have transformers. I'm not gonna do transformers today because we just have 30 more minutes. Next class, still we have to get through transformers and the different model architectures between what is transformer architecture, what is GPT architecture, and what is BERT architecture. Um, what is the encoder decoder architecture does. So we will have to go through that. Then only we will get into the coding piece of it. If you want, what I can do is we can start with the coding piece, then we can get into the theory. If you guys feel that it's too much of theory, you just want to get started with some hands-on, I can do it that fashion. But from my experience in terms of teaching, I would I would just go over a little bit theory in section 3 and section 4 alone, because this is very, very vital in terms of understanding all of this. It is very, very hard, which I understand also, but my only point is that learning all of this is just to enhance you. So the more time you give for this, the more you can be much more capable in terms of these areas. So that's what it is. But yeah, so you guys tell me how you want it to be done. I can take it in those lines as well. So that's not a big deal for me. So we can, work that out.
Okay, Bharat. Even I felt the same sometimes. Like last 3, 4 classes, it's full of
Little bit
theoretical
theory.
and vague.
Yeah, yeah.
Yeah, yeah. And the
So
problem
yeah,
is the examples also we could not imagine that one. Some of the examples okay on a high level, but some of them we cannot adapt with that examples.
makes
So we
sense.
don't know how
Okay,
to
okay.
ask questions also on that thing.
Sure, sure. No, no, that makes sense. That I get it. Okay, now I get it. So probably we'll take Kumaration's feedback. We'll start with Transformers coding in the next session, and then we will get through the theory part for Transformers in the next session. All right.
Do we need to get any subscription for all the coding that is to follow?
You guys have the Copilot subscription. Some of you took Copilot or Cursor subscription, right, for coding?
Yeah, I mean, actually, I have the free version. I didn't get the
Oh, yeah, yeah.
actual.
If you have free version, that is more than enough. That is, anyways, I'm going to give you all the source code and everything. But just in case, if you want it, if you want to practice it along with the course, you can do that as well.
Okay.
Okay. Yeah, I can tell you which subscription you guys can take. I would suggest Cursor subscription. But if you want some other sort of subscription as well, you can go for it. Anything that helps you to code, right? You can go for that subscription.
Okay.
No, Bharat, with Copilot, can we not do that?
Yeah, yeah, yeah. Copilot is also fine. Cursor is also fine. Either of it is okay. Just with the freeware Copilot also, it is fine. I'm just recommending you guys to take the subscription, because along with the course itself, you can learn. It's $10 a month. Okay, it's about like 900 rupees a month. But you get to see how you can use that AI for your better programming aspects as well, is the only point, right? So let's say you want a different neural network architecture. If you want to experiment it, if you wanted to actually get you some complicated outcomes. So then in those scenarios, the pro version works really well. So that's the only idea here.
Okay. Okay.
But just on communication, maybe the team knows or not, I don't know, but I just want to inform them. So, like anybody who is having GeoSIM or any of your friends are having GeoSIM, so you can get the anti-gravity for 18 months free. Anti-Gravity is a low-code platform where you can code similar like Codex, like our Cursor AI.
Anti-gravity is by Google basically, but
Yeah,
it's the reason I don't go with anti-gravity is because the performance of anti-gravity has been very bad. So that's the reason I generally don't prefer anti-gravity, but it is still okay for a compared to the freeware of Copilot, it is still okay. So you can go with anti-gravity as well. That is also free subscription. Like what Kumaresh is saying, you get 18 months of free subscription if you have a Geo SIM. Anti-gravity is an IDE like Visual Studio Code. Cursor is an IDE like Visual Studio Code. There is something called as Wind Surf. That is also an IDE like Visual Studio Code that we have seen thus far. So any of these platforms comes with its own AI asset. So anti-gravity is by Google. It comes with Gemini. So you can use that also if you guys want. If you guys have any questions, please put it out on the WhatsApp group as to what you want to take as such. I will just prepare a document and I'll upload it in the drive and I'll send a link to you guys as to what subscription you can take in order to work off of that subscription. Okay.
Yeah, yeah, but near Bharat. Hello.
Yeah. Please, Manikandan.
Yeah, Bharat. Just now you told something. Like, can you just put in the chat window or in WhatsApp so that we can able to
Sure.
download and keep it.
Sure. So anti-gravity, wind surf, cursor, VS Code with MS Pilot. These are some IDs along with the AI that is present over there.
And one more question, Bharat. You told that you are preparing some Google Forms and we are going to integrate all in one place where you can do the assignments, exercises like that.
Yes.
It is still ongoing, right?
Yeah. It is still in progress. Yes.
In progress. Okay. Yeah.
Once that is done, most likely it is going to take it. Ideally, I would say it is going to take at least a month to get that out. So it is going to take some time, but you guys will have access to that thing forever. So you guys can go back and do the courses. You guys can go back and do the assignments and everything as such over there itself. Okay, it has auto grading, it has everything. So pretty much. So you guys can go back and do that. So you will have access to it. So every batch, everyone will have access to that. So yeah.
Okay.
All right. So any other questions that you guys have? All right, fine then. So then we can pause here for today and let's connect next week. And we will start with transformers hands-on on next week. Okay.
Okay, Bharat. Thank you.
Okay,
All right.
thanks.
Yeah, fine. Thanks a lot,
Thank you.
everyone.
Thank you.
Thanks.
Bye.
Thank you.
Thanks.
Have a nice
Bye.
day. Bye. Bye.